Welcome to the Deep Dive. We're your shortcut for getting up to speed on really complex topics, cutting through all that information overload.
Yeah, trying to make sense of it all.
Exactly. And today, we are plunging right into the heart of modern system-on-chip designs. SOCs.
These are incredible pieces of engineering, really.
Totally. They pack everything, CPUs, GPUs, memory, specialized accelerators, all onto one tiny silicon chip.
Which brings, well, huge benefits. Size, power, definitely performance.
But integrating all that power, that creates a massive challenge, right?
It really does. The fundamental problem becomes efficient internal communication. How do all these diverse high-speed parts talk to each other effectively?
Without creating, like, a massive internal traffic jam.
Precisely. And that's where the Advanced Extensible Interface Protocol, AXI, comes in.
AXI, developed by ARM. And it's not just any protocol, is it? It's really become the standard.
The de facto standard, absolutely, for this critical on-chip communication.
And the strategic move, I think, was making it open, royalty-free.
Oh, completely. That decision was huge. It fostered massive adoption, really transformed how the industry works with IP blocks.
IP blocks, those pre-designed components.
Yeah. Suddenly, they became genuinely plug-and-play, much more so than before.
Which is a massive time saver, obviously. But it does more than that. It builds an entire ecosystem.
Exactly right. It, maybe paradoxically, enables more innovation because designers aren't constantly reinventing the wheel for basic interfaces.
They can focus on their unique value add.
Right. And within AXI, there are lots of powerful features, but one really stands out for performance optimization.
And that's our focus today. Out-of-order transactions.
That's the one. It's critical.
Okay, so our mission for this deep dive is to really unpack how AXI's transaction IDs and these reordering mechanisms work.
How they fundamentally improve system performance, overcome those traditional bottlenecks.
Enabling much higher parallelism, better throughput, and why this is just so crucial for today's really demanding applications.
Things like AI, machine learning, 5G, complex automotive systems. They all rely on this kind of efficient data movement.
All right, let's dive in.
Let's do it.
So starting with the why. Why has this advanced on-chip communication become such an absolute necessity? You mentioned integrating diverse components on SOCs.
Yeah, and it's about more than just making things smaller, though that's part of it.
Right.
When you combine CPUs, GPUs, memory controllers, specialized DSPs, AI accelerators, all on one die, you drastically cut down board size, definitely lower power consumption.
And you boost system performance compared to, say, connecting multiple separate chips.
For sure. But that very integration creates its own bottleneck, the internal data pathways.
It's like building a city full of skyscrapers, but only having narrow streets connecting them.
That's a great analogy. And think about the demands from these newer applications, AI, ML, 5G, advanced driver assistance systems.
They're data hungry, insatiably so.
Immense pressure on how data moves inside the chip. If your interconnects aren't high bandwidth and low latency, those powerful processors just sit there idling.
Bottlenecked. Inefficient.
Exactly. The interconnect becomes the limiting factor. It is the highway system for the data.
And AXI became the standard for that highway, providing this, flexible, robust way to connect all those different IP blocks.
It did.
But let's go back to the strategic genius, as you called it, of making it open and royalty-free. What was the real impact there?
It created an ecosystem. Seriously. Imagine if every IP vendor had their own proprietary interface.
Chaos, integration nightmares.
Total nightmare. Design complexity would explode, time to market would stretch out forever. AXI standardized that interface.
Making IP truly plug and play, or at least much closer to it.
Yes. Any chip designer could grab IP from different vendors and integrate it relatively easily, without hefty licensing fees just for the interface spec.
Which speeds up development cycles across the whole industry, lowers engineering costs.
Hugely important for staying competitive. And it fueled an explosion in specialized IP development because vendors knew there was a standard way to connect it.
So standardization enabling more diverse innovation. That's counterintuitive. It makes sense.
It really does.
And one of the key performance leaps AXI offers is this power of out-of-order transactions. How does that fundamentally change things?
It's a paradigm shift from strictly sequential processing. Out of order allows much more efficient use of the bus.
Reduces that effective latency.
Significantly. Instead of a single slow transaction holding everything up head of line blocking, AXI can intelligently rearrange things.
Keep the data flowing, even if one path is temporarily congested or slow.
Exactly. It directly tackles those bottlenecks.
Okay, to really get this, we need to look at the AXI fundamentals, the building blocks.
Right. At its core, it's a master-slave architecture.
Master initiates requests like a CPU needing data.
And a slave responds like a memory controller providing that data. Simple enough.
But then it gets clever with the channels.
Very clever. 5 distinct, largely independent channels.
Okay, break those down for us.
You have a write address channel, AW, a write data channel, W, and a write response channel, B. That's for writes.
Got it. Address, data, response for writes.
Then separately, you have a read address channel, AR, and a read data channel, R.
Address and data for reads. So 5 channels in total. Why so many? Why separate address and data and reads and writes?
That separation is fundamental to enabling parallelism, unlike older buses where everything might share wires and time slots.
Like AMBA, AHB maybe.
Exactly, like AHB. In AXI, read and write operations can happen concurrently. You can be sending a write address while receiving read data.
Ah, so it's like having dedicated lanes on the highway. One for writing addresses, one for writing data, one for reading addresses.
That's a perfect way to think about it. Multiple express lanes operating simultaneously. Massive throughput increase compared to a single shared lane.
And managing the traffic flow on each lane relies on the valid-ready handshake.
Yes, this simple two-way handshake is everywhere in AXI. The source asserts valid when it has information ready,
I've got something for you.
and the destination asserts ready when it's able to accept it.
Okay, I'm ready.
A transfer only happens when both valid and ready are high on the same clock cycle.
Seems simple, but critical for reliable transfer.
Absolutely. It ensures no data is lost, and importantly, it lets each channel operate at its own pace. The source doesn't have to wait if the destination isn't ready, and vice versa.
Dynamic flow control. Prevents unnecessary stalls. Keeps those independent lanes efficient.
Precisely.
Now, AXI also gets a performance boost from burst transfers, right?
Oh, definitely. Instead of one address per data item, a single AXI transaction can transfer multiple data items, beats they're called.
With just one starting address.
Right. And AXI 4 supports bursts up to 256 beats long.
256. What's the impact of being able to move that much data in one go?
It dramatically reduces the address overhead. Think about accessing sequential memory locations. You send the address once, then stream up to 256 data words.
Much more efficient than sending 256 separate addresses.
Way more efficient. It amortizes the address latency over many data transfers. Crucial for things like fetching cache lines or processing large data blocks.
Okay, bursts are powerful. Then there's the idea of multiple outstanding transactions.
This is absolutely pivotal for hiding latency. It means a master, like a CPU core, can issue several read or write commands without waiting for the first one to finish.
It can fire off multiple requests into the system.
Exactly. Keep the pipeline full. If one request goes to slow memory, the master can issue other requests, maybe to faster peripherals or a different memory bank, in the meantime.
So the bus stays busy, data keeps moving, even if some responses take a while.
That's the core idea. It effectively hides the latency of slower components, boosting overall system performance significantly.
And I can see how this all ties together. The independent channels, the valid-ready handshake, bursts, outstanding transactions, they all work synergistically.
They do. The independent channels allow multiple outstanding transactions to progress in parallel, bursts make each transaction efficient, and valid-ready manages the flow reliably.
It's also important to remember AXI isn't just one thing. There are different versions.
Right. You mainly hear about AXI 4 and AXI 4 Lite.
AXI 4 is the full-fat version, high performance.
Yeah, AXI 4, sometimes called full AXI. It's memory mapped, supports bursts, variable data widths up to 124 bits now.
Wow, 124 bits.
Supports caching hints, protection signals, quality of service, and importantly for us today, out-of-order transactions. Optimized for maximum throughput, low latency.
Then AXI 4 Lite, the diet version.
Kind of. It's a simplified subset, strictly for control and status registers, monitoring places where you don't need high bandwidth.
What does it cut out?
No bursts. Every transfer is length 1. Data width is fixed at 32 or 64 bits. No caching, no protection, no QoS usually. Much simpler logic.
So designers choose AXI 4 Lite for simple stuff to save chip area and maybe power.
Exactly. For things like configuration registers that are accessed infrequently, AXI 4 Lite is perfect. Saves gates, saves power.
But for the main data paths, memory access, GPU data, network interfaces, you need the full power of AXI 4.
Absolutely. It's a critical trade-off. performance versus area and power. Designers make that choice carefully for each interface in the SoC.
Okay, that lays the groundwork for AXI itself. Now, to really appreciate the out-of-order aspect in AXI, you suggested looking at how CPUs tackle this problem first.
Right, because the challenge is similar, bridging the gap between fast processing units and relatively slow memory or I/O.
So walk us through the old way. In-order processors.
Okay, traditional in-order CPUs execute instructions strictly sequentially. Fetch, decode, execute, write back, one after another, in program order.
Sounds logical. What's the problem?
The problem is stalls. If an instruction needs data that isn't ready yet, maybe it's a load from main memory, which is slow, the entire pipeline behind it just stops, grinds to a halt.
Head-align blocking. Like that slow car on the freeway again.
Exactly. Wasted CPU cycles, terrible for performance, especially as CPUs got much faster than memory.
And then came the revolution.
Yeah.
Out-of-order execution.
Yes, the game changer. Instructions are still fetched and decoded in program order to maintain dependencies.
Okay.
But then, instead of executing immediately, they're put into a kind of waiting room, an instruction queue or reservation station,
And they wait there until...
until their input operands are ready. As soon as an instruction has its data, it can be dispatched to a functional unit like an ALU or FPU and executed even if older instructions are still waiting.
So instruction 5 might finish before instruction 3 if instruction 3 is waiting for memory.
Precisely. But now you have results finishing out of sequence. How do you maintain the appearance of sequential execution that the software expects?
Good question. How?
That's where the reorder buffer, or ROB, comes in. Results from these out-of-order executions are stored temporarily in the ROB.
A holding pen for results.
Exactly. Then there's a final stage commit, or retire, or graduation, where results are taken from the RB and written back to the processor's official architectural state, registers, memory, in the original program order.
So the internal execution can be chaotic and out of order, but the final visible result is perfectly sequential.
You got it. It preserves the illusion of sequential execution while achieving massive parallelism and latency hiding internally.
So the bottom line for performance, what does our execution really buy you?
It directly tackles that huge speed gap between the CPU core and memory. It lets the CPU look ahead in the instruction stream, find work it can do while waiting for slow operations, keeping its execution units busy.
Overlapping computation and communication, hiding that memory latency.
That's the key. Maximize utilization, hide latency.
It sounds like it's not just a nice-to-have optimization anymore. It's essential for modern CPUs.
Absolutely essential. It overcomes pipeline stalls, helps manage data hazards, improves resource utilization. It's fundamental to performance.
And you mentioned something interesting earlier, that a lot of the benefit comes from speculation support, enabling better static schedules.
Yes, that's a fascinating point from research. While the dynamic OO execution is crucial, the ability to speculatively execute past branches, enabled by the OO machinery, allows compilers and hardware to create highly optimized static instruction schedules. Around 88% of the average performance gain, according to some studies.
So it's hardware enabling better software optimization too, co-design.
Exactly. Hardware and software working together.
Okay, and architecturally, what are the key pieces needed for OO? We have the reorder buffer, ROB, for storing results and committing in order.
Right. Then you need the instruction queues or reservation stations to hold decoded instructions waiting for operands.
And register renaming. You explained that with the mixing bowl analogy.
Yeah, register renaming is critical. It breaks false dependencies, write after read, write after write hazards.
By giving instructions their own physical storage space, even if they nominally use the same architectural register name.
Correct. It unlocks parallelism that would otherwise be hidden.
Then the final commit stage to write results back in order.
Yes, the retire or commit stage is the gatekeeper, ensuring program correctness.
And you also mentioned memory disambiguation.
Yes. That's a really complex part. Predicting whether memory operations, loads and stores, might conflict when their addresses aren't known yet. Processors use sophisticated techniques to handle this, trying to execute memory operations out of order safely.
Okay, that's a great primer on OOO in CPUs. Now let's bridge this to AXI. How does AXI achieve a similar kind of out-of-order capability for bus transactions?
The core mechanism in AXI relies entirely on transaction IDs.
IDs, like the tracking numbers on packages.
Exactly like that. AXI's ability to support multiple outstanding transactions and have their responses or data returned out of order hinges on these unique IDs tagging every transaction.
Without them, the master would just get a stream of responses and have no idea which request each one belonged to if they came back out of sequence.
Total chaos. The IDs are the key to correlating requests and responses when they take different paths or experience different latencies through the system.
So what are the specific ID signals in AXI?
There are four main ones associated with the address channels and the response data channels.
Okay.
The master sends AWID with the write address on the AUW channel,
Right as ID.
and it sends ARID with the read address on the AR channel.
Read address ID. Got it.
Then the slave, when it responds, must return the corresponding ID. It sends BD back with the write response on the B channel.
Which must match the original AWID of the write request.
Correct. And it sends ARID back with the read data on the R channel.
Matching the ARID of the read request.
Exactly. This creates that crucial link. The slave uses the incoming AOIDOR to know which transaction it's working on, and the master uses the return BDRID to match the response to one of its pending outstanding requests.
Even if response B arrives before response A, the master knows which was which because of the IDs.
That's the mechanism. Order maintained through unique identification.
But there must be rules governing how things can be reordered. It can't be a complete free-for-all, right?
Definitely not. AXI has very specific ordering rules to balance performance with correctness.
Okay, what are they?
First, there's no required ordering between read transactions and write transactions. They are independent threads.
So a read can overtake a write, or vice versa. Maximizes bus use.
Correct. Second, and this is critical, for transactions going in the same direction, so all reads or all writes that share the same transaction ID.
Okay, same direction, same ID.
They must complete in the same order they were issued by the master. The slave, or connect, must ensure this ordering is preserved for responses within the same ID stream.
Ah, so that preserves ordering for a single logical thread of operations from the master's perspective.
Precisely. It ensures data integrity for dependent operations within that thread. But the third rule is where the performance comes from.
Which is?
Transactions at the same direction but with different IDs can be completed out of order.
So if a master issues read A with ID 1, then read B with ID 2, read B's data can come back before read A's data.
Exactly. That's the core of AXI's reordering capability. It allows parallelism and latency hiding across independent threads, different IDs, while maintaining strict ordering within a single thread, same ID.
That's a really elegant balance between performance and correctness.
It is. It's a very well thought out part of the specification.
Now, in complex systems, you don't just have one master and one slave. You have AXI interconnects, like crossbars, connecting multiple masters to multiple slaves. How do they handle IDs?
The interconnect plays a crucial role in ID management, especially for global uniqueness.
Because master 1 might issue a request with ID 5, and master 2 might also issue one with ID 5.
Right. The interconnect needs to distinguish those. A common technique is for the interconnect to prepend or append a unique master number or port identifier to the ID received from the master.
So master 1's ID 5 becomes, say, global ID 0 by 105, and master 2's ID 5 becomes global ID 0 by 205 as they travel through the interconnect.
Something like that, yes. This ensures every transaction flowing through the interconnect has a globally unique ID. The interconnect then uses these global IDs for routing and arbitration.
And it has to strip that extra info off before sending the response ID back to the original master.
Correct. It needs to map the global BDRID back to the original AWIDRID that the specific master expects. This abstracts the complexity of the wider system away from the individual master and slave components.
Very clever. Makes the whole system scalable.
It does. It allows these out-of-order benefits to work effectively in large, complex SOCs.
Okay, so we've got the how IDs, ordering rules, interconnects. Let's talk payoff. How does this AXI out-of-order capability tangibly enhance performance in SOCs? What's the #1 benefit?
I'd say the biggest one is latency hiding. We touched on this, but it's worth emphasizing.
Right, allowing masters to issue new commands while waiting for slow ones.
Exactly. Accessing main memory or slow peripherals can take hundreds of cycles sometimes. If the master had to wait, the bus would be idle performance tanks.
But without standing transactions and O completion.
The master keeps issuing requests, the bus stays busy processing other transactions, effectively hiding those long latency periods under useful work. Huge for memory-intensive tasks or systems dealing with lots of concurrent requests.
That naturally leads to increased throughput and parallelism too, right?
Directly. Combine OO with the separate read-write channels and burst transfers. You're maximizing the amount of data moving across the bus in parallel at any given time.
Significantly higher data throughput overall.
Absolutely. Think about network processing. Maybe different packet flows get different AXI IDs. They can be processed in parallel. Responses come back out of order, maximizing link utilization.
Or image processing, fetching different tiles of an image concurrently using different IDs.
Perfect example. Accelerates the whole frame processing time. These are real-world scenarios where OO makes a massive difference.
What about resource usage inside the chips themselves?
Ooh, helps there too. Internal buffers and processing logic in masters and slaves don't sit idle waiting for the next sequential thing. They can grab any ready transaction regardless of its original issue order.
Better utilization of those internal resources.
Yeah, and it facilitates better load balancing across multiple slaves. The interconnect can route transactions independently to slaves that might have different response times, keeping everything humming along more efficiently.
And we can measure this, right? There are specific metrics that improve.
Definitely. You look for reduced average read-write latency because faster responses can bypass slower ones.
Yep.
Increased bandwidth, more data per second.
Higher valid cycle counts on the bus, showing it's being used effectively.
Exactly. And conversely, lower busy cycle counts where components are stalled waiting, plus just the total transaction count or data volume moved in a given time.
But it's not just about speed, is it? There's a broader PPA picture. Power, performance, area.
Right. Reducing idle cycles also helps save power. If components aren't stalled, they can potentially enter lower power states faster, or the whole system might run at a lower frequency voltage, dynamic voltage, and frequency scaling, DVFS.
Which is critical for battery-powered devices or even reducing heat in data centers.
Absolutely. So OO contributes to the whole PPA optimization, which is the name of the game in modern SOS design, especially for those demanding AI, 5G, and automotive applications.
Okay, the benefits are compelling. But let's be realistic. Implementing something this complex must have challenges. What's the big one?
Verification. Without a doubt, verification complexity explodes.
Because things don't happen in a predictable order anymore.
Exactly. Transaction responses can arrive in almost any order depending on latencies, arbitration, QoS.
Yeah.
Traditional simulation methods based on fixed sequences are insufficient.
You have to cover a massive state space of possible interleavings.
You do. Ensuring correctness under all possible reordering scenarios requires advanced verification techniques, sophisticated test benches, and often huge amounts of simulation time or formal methods. It's a major engineering effort.
And that non-determinism must increase the risk of deadlocks.
It certainly does. In complex multi-master, multi-slave systems, the flexibility of OO opens up more possibilities for circular dependencies.
Transaction A waiting for B, which is waiting for C, which is waiting for A gridlock.
Yep. The interconnect needs to be designed very carefully with robust arbitration schemes, potentially timeout mechanisms, maybe even dedicated transaction monitoring units, TMUs, to detect and sometimes break these deadlocks. Debugging them can be incredibly difficult.
You mentioned QoS quality of service, allowing masters to prioritize transactions. How does that interact with OO and IDs? Is there a catch?
There is a subtle but critical catch. AXI rules state transactions with the same ID must complete an order.
Right, we covered that.
But QoS allows the interconnect to prioritize transactions. So what if a master issues 2 writes, both with ID 5, but gives the second one a higher QoS priority?
Uh-oh. The interconnect might reorder them based on QoS.
Exactly. And now the responses could come back out of order, violating the same ID ordering rule.
So how do designers handle that?
The standard recommendation is, if transactions from a single master need different QoS levels, they must be assigned different transaction IDs. That puts them into separate ordering threads, avoiding the conflict. It's a constraint designers have to remember.
Seems like a potential gotcha. And the masters themselves need to be pretty smart to handle all this.
Oh, absolutely. The logic inside an AXI master that supports multiple outstanding transactions in O completion is complex.
It needs buffers to store info about all the requests it sent out.
Right. State machines to track them, logic to match incoming beads and RIs to the stored requests, and then often logic to reorder the received data back into the original program order before the core logic sees it.
A significant amount of overhead within the master IP. Yeah.
It is. It adds area and complexity to the master design.
And underpinning all of this is data integrity. Errors must be caught.
Non-negotiable. AXI has response signals, BRSP for writes, RASP for reads that indicate success, okay, or various error conditions, S-over, deser.
Slave error, decode error.
Right. Masters must check these responses. But errors can also happen within the interconnect or due to protocol violations.
That's where things like transaction monitoring units come in again.
Yes, TMUs can sit within the interconnect fabric and actively monitor traffic for things like timeouts, requests that never get a response,
Mhm.
illegal signal transitions, ID mismatches, potentially triggering alerts or recovery actions to maintain system stability.
Okay, given these benefits and challenges, what are the best practices? How do designers get AXIOO designs right? Starting with configuration.
Careful configuration is key. Choosing the right AXI data widths for the required bandwidth. Optimizing burst lengths longer isn't always better if it causes blocking.
And using QoS effectively, not just setting everything to high priority.
Right. Using QoS thoughtfully to prioritize genuinely critical traffic, like maybe real-time audio samples over bulk data transfers. It requires understanding the system's traffic patterns and bottlenecks.
Then comes verification. You said it's complex. What are the standard methodologies?
Thorough verification is non-negotiable. A bug found after silicon tape-out is incredibly expensive, millions of dollars, months of delay.
So what tools do teams rely on?
The Universal Verification Methodology, UVM, is the dominant standard. It provides a framework for building powerful, reusable test benches.
Things like constrained random stimulus generation.
Yes, creating vast numbers of valid and invalid scenarios automatically. Plus scoreboarding to check data correctness, functional coverage to measure what's been tested, assertions to monitor protocol rules. UVM is essential for tackling AXI complexity.
What about formal verification?
Formal methods are also crucial. They use mathematical techniques to prove properties about the design rather than just simulating test cases.
Like proving the deadlocks are impossible under certain conditions.
Exactly. Or proving that the AXI ordering rules are never violated. Formal is extremely powerful for finding corner case bugs that simulation might miss, especially related to concurrency and ordering.
And then there's speeding things up with hardware.
Hardware-assisted verification, HAV, techniques like hardware emulation or FPGA prototyping.
Running the design on actual hardware, much faster than simulation.
Orders of magnitude faster. This allows running much longer tests, including real software workloads, much earlier in the design cycle. It's key for finding system-level bugs and enabling early software development. Part of that shift-left philosophy, find bugs sooner.
But even with all that, bugs happen. Debugging timing and ordering issues in these fast O systems must be tough.
It is one of the hardest parts of SOS design. But you have tools.
Like waveform viewers.
Absolutely essential. Tools like DVE or SimVision let you visualize the AXI channel signals over time, trace transaction IDs, see the handshakes. You spend a lot of time staring at waveforms.
I bet. What if the parallelism makes it too hard to follow?
Sometimes you need to simplify. Enable verbose logging in your UVM environment to get text traces, or even temporarily configure the system to serialize transactions, forcing things into a more predictable order just for debug, to isolate a specific interaction.
And for debugging on actual silicon or FPGAs.
You rely on logic analyzers to capture the actual digital signals on the chip's pins or internal probe points. Oscilloscopes for looking at signal integrity, the analog quality of the signals.
It sounds like you need a very systematic approach.
You do. Reproduce the problem reliably. Gather all the information, waveforms, logs, formulate hypotheses about the cause, test them, isolate the root cause, implement a fix, and crucially, verify the fix thoroughly. It's detective work.
So wrapping this up, it's incredibly clear that AXI, especially with its out-of-order transaction support and ID management, is fundamental to modern high-performance SOSs.
It really is a cornerstone. It's the sophisticated plumbing that allows these incredibly complex chips to function efficiently.
Letting masters issue multiple requests, getting responses back non-sequentially. It all works to hide that dreaded memory latency.
Maximize bus use, boost throughput, enable parallelism. It keeps the whole system fed with data.
And the key enablers are those unique transaction IDs, AWID, ARID, BID, ARID, BRITC, allowing correlation even when things arrive out of sequence.
Indispensable. They provide order within the apparent chaos, ensuring correctness.
And AXI's evolution reflects where SOC design is going, more complex integration, chiplets, AI everywhere.
All demanding smarter, faster, more flexible interconnects. AXI has evolved to meet those needs.
And yes, there are challenges, verification complexity, deadlock potential, but the industry has developed powerful methodologies to manage them.
UVM, formal HAV, careful design practices, robust interconnects. These challenges are understood and addressed systematically.
The push for performance and efficiency isn't stopping. AI, automotive, 5G, they'll keep driving protocols like AXI forward.
No doubt. We'll see continued evolution focusing on even higher bandwidth, better power efficiency, maybe more sophisticated QoS or dynamic adaptation.
So a final thought for you, our listener. Think about how AXI takes all these separate, potentially out-of-sync requests and orchestrates them into an efficient, coherent flow. It's like a conductor leading an orchestra.
Different sections playing different parts at different times, but it all comes together harmoniously.
Where else in technology or maybe even daily life could applying this principle of managed out-of-order processing, guided by clear rules and identifiers, lead to greater overall efficiency and harmony? Something to ponder.